Good morning, everyone. I'm Daniel Taiwo. I am a PhD student from Imperial College, London, under the supervision of Dr. Catrin Davies. And yeah, as the title shows, I'll be giving a presentation on the effect of temperature on the fracture toughness properties of Askar's DP800 steels. So I'm going to begin with a brief overview of the context, and then I'll talk about some metallographical work that I've done to characterize ASCAS DP800 steel slabs, and then I'll talk about some fracture toughness tests that I've conducted and the conclusions that I have gotten from them. So to begin with the reason why observing the fracture toughness properties of ASCAS DP800 is important in this case is due to the phenomena of clinking and reheat cracking. So these phenomena are characterized by brittle, audible fracture of steel slabs after they have been continuously cast. And this fracture occurs perpendicular to the direction of casting and propagates through the thickness of the slab. And the aim of my project is to further an understanding of these mechanisms that result in clinking and reheat cracking. So, as I mentioned, they happen. The phenomenon happens after continuous casting. There are a number of process routes that a slab can take once it's out of the continuous caster. You can hot charge it and keep it at a temperature above its transition temperature. But clinking and reheat cracking often occurs when it's either cooling down in a slab yard or being reheated in a reheat furnace. So it has been shown that clinking and reheat cracking is linked to thermally induced stresses due to non-uniform cooling within the slabs. And this has a low frequency of occurrence, about 1 in 1,000 slabs or thereabouts. But when it does happen, it can be quite significant. Another factor to consider is that there are casting defects introduced by continuous casting that can be exacerbated by DP800 steel's composition, which can overlap with the peritectic range. So a bit more about continuous casting. Essentially, you're taking molten steel, you are putting it into a water-cooled copper mold, which initiates the solidification process, and then this is then extruded out as the solidification continues. It's guided through. When the solidification is complete, then it's cut to length. And due to the nature of continuous casting, you end up with an extremely anisotropic microstructure. So on the outside, which cools the quickest, you have the chill zone with the smallest grain sizes that are randomly orientated. But as you move further in, you encounter the columnar zone, which has textured grains that are aligned with the direction of heat flux. And in the middle, you have equiax grains, which again are randomly orientated. Grain size wise, you have the smallest grains in the chill zone. Largest grains generally I've found are in the columnar zone, and in the middle, you have the equiax zone. Another thing to take into account is the appearance of ductility troughs, which have been known to occur in certain cast steels. Now, these are characterized by a reduction in ductility in a temperature range. There are multiple zones for this, but the one probably most of most concern is in the lower temperature range, because this can be as low as 600 degrees. And these can be attributed to ferrite formation upon cooling, which then preferentially deforms and forms voids, which then coalesce and cause intergranular cracking, but it can also be due to grain boundary sliding. So to summarize the context, you've got a peritectic composition from DP800 steel, anisotropic microstructure due to the nature of continuous casting, which can also introduce casting defects into the material. And then you've got a ductility trough at certain temperature ranges. All of these are interacting in a slab, which is subject to thermal stresses upon cool down or reheating. So before looking at the fracture toughness properties, it was important to observe the extent of the solidification zones that I've just discussed. So some metallographic work was conducted, and quite a large area of a DP800 steel slab was polished and etched to see the extent of the solidification zones. And the transition between the chill zone and the columnar zone here is quite clear in the top picture. As you can see, quite small grains, less than 3 millimeters squared, making way for quite large columnar grains, which are aligned. You can see in the bottom image here, they are aligned with an axis down into the page. Another takeaway from this is that the microstructure of as-cast DP800 is bainitic ferritic. This is to be expected. You can see a lot of allotriomorphic ferrite forming in the grain boundaries. But there is also perlite forming at the grain boundaries, no doubt because the diffusion rates are higher. So as we move down the slab, the columnar zone makes way to the equiax zone, relatively in the center of the slab, which an average grain size of 3 millimeters squared. And then this again moves down to another columnar region and the chill zone in the bottom. So having determined the solidification zones, I was able to extract samples for testing. And that's exactly what I did. And some Sharpie V-notch samples were extracted from 6 different depths in the slab, encompassing all 3 solidification zones. These were tested from room temperature all the way up to the melting point temperature of the steel. And these were oriented so their crack plane is parallel to the XY plane, mimicking the propagation and crack plane of clinking and continuous casting. Another thing to note is that because in situ heating was not feasible, a temperature loss study was conducted for each of the target temperatures to ascertain the how fast the temperature loss rates and ensure that the tests weren't too far away from the target range. So results-wise, as to be expected with ferritic or bainitic steel, you can see a clear brittle to ductile behavior happening here as you reach a peak, but you don't actually get an upper shelf due to the effect of thermal softening that happens quite soon afterwards. And interestingly, the ductile to brittle transition temperature for each of the solidification zones were relatively similar, though you would expect, which are larger in the columnar zones, which have much larger grains than the chill zone, you'd expect the columnar zones to have higher ductile, brittle to ductile transition temperatures. But there's clearly another mechanism in effect here because they are relatively consistent. Now, the actual temperature values have been normalized. Apologies, because they are proprietary information of Tata Steel. But you can also see an apparent choppy energy trough at about 0.4 normalized temperature here, which suggests perhaps there is a ductility trough effect here, lowering the toughness of the samples. But with choppy samples, there are lots of variability in measurements, so this does need to be corroborated, which is what I have set up to do. And so I do have some ongoing J1C testing with 3-point band SEMB samples to basically test the temperature range up to half of the melting point of the steel as well, and to see whether or not there is actually a ductility trough present in the material. And so far, some room temperature tests here show type 3 unstable porphyrin fracture. This is actually relatively common. There has been some work done on electrical steel, and this behavior does show up here. But I attribute it to an unstable fracture being arrested by a crack by a grain boundary, but more tests needed to be done to actually make that a definite mechanism. But yeah, so the fracture behavior is common in all solidification zones, even as you can see from the 3 force displacement curves here, and the valid J1C values were able to be obtained, which were low, less than 20 Newton per millimeter. At higher temperatures, preliminary studies are showing, as to be expected, significant increases in fracture toughness. The fracture toughness is actually about doubled, about 2.5 times the room temperature values, but you do still see pop-in fracture, though it's not as common and it's not to as high a magnitude. There is a lot of plastic collapse happening for many of the tests that I've conducted at higher temperatures, and the crack sometimes actually does not grow. So that's also an interesting effect of temperature. But yeah, the aim is to complete those tests to the temperature range suggested by the Sharpie tests, where a ductility trough may be occurring, to see if that is actually the case. And in summary, Sharpie testing is indicating a fairly high ductile to brittle transition temperature to be expected with the large grain sizes we see, and fracture toughness tests are corroborating the increase in temperature, the increase in toughness as well. Yeah, thank you.
Thank you, Daniel.